Hello, my name is Paul Wilson and I am here with my colleague David Clement, and we are the engineers in control. This is the fourth talk in our series, Control Systems 101. And talk number 4 continues looking at system dynamics and moves towards differential equations. You recall from talk number 3, and I showed you this chart. And this is our chart of energy types, but this time I've put in the differential equations. So let's have a look at friction resistance, which is a passive, and we've got electrical resistance, a linear equation. For mechanical we have friction and velocity, again a linear equation. For fluid flow, we have fluid flow friction based on the driving force pressure, and we have a resistance to heat flow based on the resistance. But when people teach this in universities, they don't talk about resistance, they talk about conductivity. For kinetic energy storage, which is reactive, we have inductance, and that's a differential equation as the driving the voltage is the driving force for electrical. For mechanical we call it force, of course, that's the driving force. For fluid flow the driving force is the pressure, and as I mentioned last time, for heat there is no such thing as thermal inertia because heat does not have mass. For potential energy storage we use integral equations, and for electrical the capacitance is an integral of the driving force, the voltage. We have spring tension for mechanical, again we have the driving force. For fluid flow, storage at altitude gives us potential energy, and we have pressure, and for heat storage the driving force is the temperature difference. The way we generate a differential equation is to find a balanced equation for the system. And I have a chart here with some outline of some balanced equations. So in an electrical circuit, Kirchhoff's laws tell us that all the positive and negative voltages around the circuit add up to 0. And it's the same with Kirchhoff's current laws, that all the currents in and out of a junction add up to 0. Surprisingly, and not surprisingly to me anyway, Kirchhoff's laws also apply to flow rate, so that the pressures all add up in flow rate, and the flow rate currents in and out of a junction all add up to 0. In a mechanical system we have Newton's laws of motion that tells us that all the forces add up to 0. Every force has an equal and opposite reactive force. We can still use Newton's laws in fluid flow, and we can use Kirchhoff's laws in fluid flow as well as balance equations. And Bernoulli added an interesting insight that the pressure drops as the velocity, or the flow rate if you like, increases. In thermodynamics, the dynamics are governed by Newton's law of cooling, which tells us that the rate of transfer of heat is proportional to temperature difference. And that bloke Newton gets in the way all the time, doesn't he? For the balance equations, I have another chart here that's slightly different. And I just want to point out that we can use the driving force, or all can use the current or flow rate. So in this chart we can balance the force along the top here, but we can also balance velocity, electrical current, flow rates or heat flow. So we have a choice with our balance equations with electrical voltage or current, mechanical force or velocity. With flow rate we can balance pressures or flow rates, and with heat we can balance temperature differences and heat flow. And in fact, with electrical, Kirchhoff's laws, we can use Kirchhoff's voltage or Kirchhoff's current law. In the mechanical system, we can use velocities or forces, and we have that choice. With fluid flow, same with Newton's laws, but we can use flow rate or pressure in our balance equations. And with heat flow it's the same, we can balance temperature differences or the actual flow of heat. Temperature control is very simple, of course, because it doesn't have inertia, and so thermal systems or temperature control systems tend to be rather easier than the other types of systems. Because all the different processes are virtually identical, it is simple to combine different systems into one single differential equation. And I'll show that in the following photograph. So for process control, we do have different systems within the same process, and here's a very good example. This is a thickener underflow pump set that I photographed on a mine site. We have an electric motor with inductance and resistance, so there are two reactive components in this. We also have a motor pump set, so we have in fact a chain drive on this driving the axle of the pump, and so we have inertia, and we also have friction in that process. And then we have fluid flow. Here's the inflow and the outflow pipe. It actually pumps a slurry, and so we have the inertia of the fluid flow in the pipe. So in this system we have a combination of electrical, mechanical and fluid flow. We have at least three reactive components. We have motor inductance, the motor and pump set inertia, and the inertia of the fluid flow. So we're going to leave it there at this time for talk number 4, and in talk number 5 we shall examine an electrical filter and develop a differential equation for a filter. So we hope you tune in and watch talk number 5. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement. All rights reserved.